So in the last session, if you remember, we were talking about principal component analysis, which is one of the dimensionality reduction techniques, right? So in last session we talked about PCA. I have given you an idea about PCA, how actually it works and what it does, right? So principal component analysis is the dimensionality reduction technique is one of the dimensionality reduction technique which we have talked about in the last session. And I told you, if you get a time, I will show you the implementation for PCA. Right. Today, what we will do is we will try to talk about the remaining point, and that is nothing but this one: distributed stochastic neighborhood embedding. That is PSNE. Now, what is this? SNE is nothing but stochastic neighborhood embedding. So, what is this? Let's try to talk about that particular point. That is the last point, and we will be done with unit 1 as well as unit 2. Okay, because I told you yesterday only, I discussed the points from this one, and then I actually once again came to this particular unit. Okay, those who are present, they know that. Right. So to discuss about this last topic, distributed stochastic neighborhood embedding or TSN, let me tell you from the start itself what it is. Let's try to see what is that stochastic neighborhood embedding actually is with a simple example. For that, I will try to show you simple diagram. Let's see what is that, and let's hope you will understand it, because there is some mathematics also involved in stochastic neighborhood embedding, which is actually not mentioned in your syllabus, right? So let me try to explain you what is this stochastic neighborhood embedding. So TSNE, it is actually called as. Now what is TSNE? Let's try to start with that first. So, for those who joined late, let me write down the full form of this. It is nothing but stochastic neighborhood. So there are different gradient methods also you people might be aware about. So stochastic neighbor embedding or stochastic neighborhood embedding it is called. Okay, that is the full form of SNE. Now, what is this? So, T distributed, actually it is called as T distributed stochastic neighbor embedding. It's actually a non-linear dimensionality reduction algorithm. I will write it down as, remember this word, it's a non-linear dimensionality reduction algorithm. So that means this is also a dimensionality reduction algorithm as similar to PCA, but there is a difference. There is a difference between PCA and TSN. Okay. This is also used for the same purpose for dimensionality reduction technique. For dimensionality reduction, I can say, but it is specifically used for exploring high dimensional data. So what I can say is it can be used for exploring high dimensional data. Whenever we say dimension, that means we are talking about features. So in yesterday's example, I told you there are 100 features. For example, there are 500 features. So definitely in that case, this TSNA is going to come into picture. Now, which one is better? Whether PCA is better or TSNA is better? That we will see at the end actually. So PCA or one should make use of TSN, because the purpose of making use of both the algorithms is actually same. That is nothing but dimensionality reduction. The purpose is same, but which one to make use of? Let's try to talk about that one also later on. But let's first of all see what is actually this TSN and what mathematics is involved behind that, and what can be the steps to carry out or to implement this TSN algorithm. Right. So TSNE or T distributed stochastic neighbor embedding, it's a machine learning algorithm for we can say visualization based on stochastic neighborhood embedding. There is a concept which is called as stochastic neighborhood embedding, which was originally developed by some people. I can remember the name, like name of the person who developed that particular technique was Sam Roweis, something like this. I think Roweis. Sam Roweis is the person, and one more person is there. Name is Joffrey. These are the two people who came up with the idea of stochastic neighbor embedding, and based on that, this algorithm is there, right? And there is one more person who actually proposed the T-distributed variant. So this is actually based on T-distributed variant. See, there is a topic in statistics which is called as T-distribution. Some of you might have heard about something called as T-test, right? Hypothesis test. Some of you might have heard about hypothesis test. So this is related to statistics actually. So what this PSNE makes use of is PSNE makes use of something called as t-test. It's a theoretical concept. So this PSNE algorithm is actually based on t-distributed variant, and this t-distributed variant was proposed by a person whose name was Van der. This is the name of the person who proposed that, Van der Matten. This is the name of the person who proposed this particular thing for stochastic neighbor embedding algorithm. The basic point is that this algorithm is actually used for exploring high dimensional data. That means t-distributed stochastic neighbor embedding is a machine learning algorithm for visualization, which is based on stochastic neighbor embedding. Right? This is a technique which I am trying to talk about. Okay. Now it's an unsupervised algorithm, I can say. This is PSNE algorithm is unsupervised algorithm. Remember that. It comes under unsupervised approach or unsupervised machine learning, we can say. Right. So this PSNE is an unsupervised machine learning algorithm. It's non-linear. Right? If you remember about PCA, principal component analysis, we use PCA actually, and I say that it's a pre-processing algorithm. It is not going to give us the output directly. But here in this case, this PSNE is actually unsupervised. It makes use of unsupervised approach. It's non-linear technique, and it is primarily used for data exploration. So the primary use of PSNE is data exploration. Why to do data exploration? Just to understand the data in detail, we can say, and just try to make some sense out of that data. That's why we can make use of this kind of a technique that is PSNE. Okay, so in simple terms, PSNE gives you a feel or intuition of how the data is actually arranged in high dimensional space. Right? See, as a human we can see till three dimensions, for example, or we can understand till three dimensions. But if the data is in multi-dimensional or high-dimensional space, obviously it will be very difficult to understand. So that's where this kind of techniques are going to come into picture, like PSA. So it gives you a feel or intuition of how your data is actually arranged in high-dimensional space, right? So t-distributed stochastic neighbor embedding, it's a non-linear dimensionality reduction algorithm which is used for exploring high-dimensional data. Okay, so it is also unsupervised non-linear dimensionality reduction and data visualization technique. So many people call it as data visualization technique. Now, if you try to compare PCA and if you try to compare this PSNE, so PCA, talking about PCA, it does not work well as compared to PSNE in some cases, right? And PSNE is actually one of the best dimensionality reduction techniques. We will see how actually it differentiates, but yes, generally that's what actually happens. Now, one of the most major differences between PCA and PSNE is that it preserves only local similarities. PCA preserves only local similarity, where this algorithm preserves large pairwise distance, considering the maximum variance. Okay, so that is a basic difference. And again, in terms of working or in terms of implementation also, they are going to differ. Both PCA as well as PSLE, definitely they are going to differ in terms of implementation. Now, talking about other things, like as I told you that this t-distributed stochastic neighbor embedding is a machine learning algorithm for visualization, which is based on stochastic neighbor embedding, originally developed by these people, right? So it's a non-linear dimensionality reduction technique. That means if your data is linear, that means if you are going to plot a graph for your data, right, and more or less your data seems to be in linear fashion, right? So that for this kind of a data, it should not be used. But for non-linear data, one can make use of PSNE kind of a technique. So that's why it's a non-linear dimensional reduction technique, which is well suited for embedding high dimensional data for visualization in low dimensional space of 2 or 3 dimensions, I guess. Right? And specifically, this TSNE models each high dimensional object by 2 or 3 dimensional point in such a way that similar objects are modeled by nearby points, and dissimilar objects are modeled by distant points, I can say, with high probability. It means what? For example, see, if your data set is something like, obviously it will not be in 2 dimensions. right? Suppose you have some data points, and maybe the data points are something like this. A lot of data points are there like this. Okay. So as it's high dimensional data, so you are going to see a lot of data points like this. Now, where this TSNA is going to come into picture, TSNA is going to help you to visualize this particular data in high dimensional space. That means maybe it can go and it can convert it into low dimensional space. Right. Now, what TSNA is going to be here is, it is going to, for example, maybe for example, this is the point, right? This is the point. So it is going to do what? It is going to form the groups or the clusters. So it will tell you, okay, the point nearer to this particular point which I have marked as red is this one, suppose. Another point is this one. So it is going to make the groups like this, right? And other points are going to be at some distance. So it is going to make use of some distance formulas or distance equations. Now, how to find out the distance between 2 points in a high dimensional space? I already told you. How to find out the distance between 2 points in a plane? We already discussed that. This is what TSN is going to make use of. So instead of that distance, what it is going to do is, once it finds out the distance, it makes use of probabilities, right? And how it is going to make use of the probabilities, or why it is going to make use of the probabilities? Because if it finds out this particular point, and if it finds out the distance between these 2 points, right? So then it will go and it will try to find out the probabilities for other points, whether they are nearer to this point, or they are at distant from this point, or at far away from this point. So which are the different methods with the help of which you can find out the distances? Most of the times the TSNE algorithm, it makes use of something called as Euclidean distance. Okay, so Euclidean distance is the basic formula which I think told you yesterday only. So how to find out the Euclidean distance between the 2 points in the plane? So I told you that if there are the points P1 and P2, you can find it out like this: x1 minus x2 whole square plus y1 minus y2 whole square. This is how we can find out the distance. So it's a two-dimensional data we are expecting, but if it's an n-dimensional data also, I shown, right? Dot 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 and so on, you can find out the distance between all the points with the help of Euclidean distance. So this is the distance which TSNE also makes use of. But again, it is not like that there is only Euclidean distance which is available to find out the distances between the points in the plane. There are other methods also, or other formulas also. For example, you might have heard about something called as Hamming distance. Yes, Hamming distance is also one method which can be used to find out the distances between the points. If you are aware about Hamming distance, maybe I think you are aware about that. So how to find out the Hamming distance? So Hamming distance actually makes use of only two values, either 0 or 1, right? So it makes use of only two values, and it is used for categorical variables actually, right? So for example, if I want to give example like zip code, just take an example of zip code, right? Now zip code is value 1, value 2, value 3, and so on. And zip code will be repeated again and again, right? Because if the address, if the city is repeated, zip code is going to be repeated, for example, or if the area is repeated, zip code is going to be repeated. So value 1, value 2, value 3, value 1, value 2, and so on. So what's going to happen is, Hamming code, how it is going to be used? Suppose if value 1 is not equal to value 2, right? Then Hamming distance is equal to 1, right? Otherwise, if value 1 is equal to value 2, then Hamming distance is going to be 0. That is, they belong to the same class. That means they are same. Hamming distance equal to 0 means this value and this value, for example. So they belong to the same class. So this is how Hamming distance is actually used. And so this is one way to find out the distance. Hamming distance is another way to find out the distance between the points in the plane. And then there is something called as Manhattan distance also. So you might have heard about this particular thing also, Manhattan distance. Okay. So how to find out the Manhattan distance between the points? So you might be knowing that the formula goes like this. So magnitude of x1 minus x2 plus magnitude of y1 minus y2. Something like this is the formula to use to find out the Manhattan distance. So when do we use Manhattan distance? Actually, it is used for a data which is of very, you can say, for a very big data size. Manhattan distance is actually used to find out the distances between the points. And what is this magnitude? It is actually absolute difference. That means it will be positive, right? It's actually absolute difference. That's why I used this magnitude sign, right? So we have different ways. Euclidean distance you can use, Hamming distance you can make use of. Manhattan distance also can be used to find out the distance between the points of the plane, right? So, but yes, as I told you that this PSNE by default makes use of Euclidean distance to find out the distances between the points, and then it is going to come up with some clusters like this. So it is going to create the groups, right? So it will create the groups, the points which are similar, it will group them in the same group, we put them into the same group, and then according to that, then it is going to convert high dimensional data into low dimensional data. This is the basic idea behind is PSNE algorithm. Right? I hope you people are able to understand what is the basic purpose of PSNE. Let's try to focus on some more points related to PSNE. So definitely, whatever PCA is going to do, same is the purpose for TSNE also, but there is a difference. There is a difference actually in the working. So let me clear this. Now, as I told you that it is going to make use of Euclidean distance. Along with that, it makes use of some other methods, right? So as we have seen that it's a machine learning algorithm for visualization, which is based on some technique called as a stochastic neighbor embedding technique, right, which is developed by some people. So it is basically suited for embedding high dimensional data for visualization in low dimensional space, maybe of 2 or 3 dimensions, I can say. And specifically, it models each high dimensional object by 2 or 3 dimensional point in such a way that similar objects are modeled by nearby points, and dissimilar objects are modeled by distant points with high probability. Okay, so that means it makes use of the concept of probability. So the TSNE algorithm, it comprises two main stages. The first stage of TSNE is going to be to construct probability distribution. So first step is going to be to construct probability distribution. As I told you that this TSNE algorithm is going to make use of probabilities. The first step itself is going to be constructing the probability distribution over pairs of high dimensional objects. In what way? In such a way that similar objects are assigned higher probability, while dissimilar objects or points are assigned lower probability. Right? As simple as that. The objects which are similar, they will be assigned higher probability, and the objects which are not similar, they will be assigned a lower probability. And the second point or the second stage in case of TSN is that TSNE actually defines similar probability distribution over the points in low dimensional band. So if it's a 1 dimension, 2 dimension, or low dimensional data, right? So what it does is it defines a similar probability distribution over the points in low dimensional map, I can say, and it minimizes something which is called as KL divergence. Now, KL divergence itself is a separate topic actually. So along with the probabilities, TSNE makes use of something called as KL divergence, and KL divergence stands for something like pullback divergence, or pullback. L stands for something LEIBLER, labeler divergence. That is called as KL divergence. Okay. So along with probability, this PSNE makes use of KL divergence between two distributions with respect to the locations of the points in the map. While original algorithm makes use of, I told you, it makes use of Euclidean distance, right, between objects as the base of its similarity matrix, and this can be changed appropriately as per the requirement, right? So the TSNE has been used for visualization in wide range of applications. If I want to talk about the applications where this kind of algorithm can be used, there are a lot of applications which can be there. For example, which includes security, or specifically if you talk about computer security, right? So if there are different intrusions, different viruses. Now, if you are able to catch one type of virus, how many other viruses or intrusions are similar to that kind of a virus, right? So you can go and you can actually group those things in one group, right? So computer security can be one application. With the help of this TSNE, one application of TSNE, or in research, I can say computer security research, you can make use of this TSNE algorithm. Or maybe if you want to go and if you want to analyze the music, what type of a music, right? So music analysis, for music analysis even you can go and you can actually make use of TSNE, because here also you can make the groups depending on what type of a music is it. You can go and you can actually group all those files together, right? And in talking about healthcare domain, you can make use of this PSNE algorithm for cancer research, and it is actually being used in this particular domain. Again, that's again totally a different topic. Okay, it's a huge area itself. So yes, in this cancer research specifically, this PSNE can be actually used. Bioinformatics, again, this is also one area where this kind of algorithm can be used. Okay, so and obviously, in case of signal processing, or I can say biomedical signal processing, those people who will go for their research maybe in future, or maybe those people who are thinking about MS, definitely uh, these kind of algorithms are going you are going to come across biomedical signal processing. This kind of algorithm can be used. Okay, so whether you are going to play with image data, video data, you are going to come across this particular algorithm. Okay, so it is actually it is often used to visualize high dimensional or high level representations learned by an artificial neural network. Okay, so artificial neural network is actually a part of deep learning. Again, that's again a separate topic actually. So in case of deep learning, actually we learn about neural networks. And when we learn about neural networks, there are different types of neural networks. There's something called as ANN, artificial neural network. There's something called as CNN, convolutional neural network, and there's something called as RNN, recurrent neural network. So this itself is a separate topic actually. We will not go into the deep of that. Okay. We will just talk about this PSN and try to understand about how the working, how actually it works. So while the TSNE actually plots, TSNE plots often seem to display clusters, that is groups. The visual clusters can be influenced strongly by the parameterization, and therefore good understanding of the parameters for TSNE is necessary. So whenever we talk about these parameters, I mean to say the features. So if you want to go and if you want to apply this TSNE algorithm, obviously knowledge of data is very important. So such clusters can be shown to even appear in non-clustered data, and thus we can say maybe false findings can be there. So interactive exploration may thus be necessary to choose parameters and validate the results. So there are different demonstrations in TSLE, which is often able to recover well-separated clusters with spatial parameter choices, right? So many times you will see a term which is called as spectral clustering, which is used whenever we talk about this PSNE algorithm. Okay. Now, this is a basic idea about PSN. Talking about the mathematics which is involved, so definitely we're gonna see some mathematical equations here. For example, see what happens is if I want to represent this particular algorithm mathematically, for example, you are given a set of some n-dimensional objects. Just imagine that you have been given the set of n-dimensional objects. Okay, maybe x1, x2, x3, x4, and so on like this. So just put it down here. We have been given the set of n-dimensional objects x1, x2, x3, and so on till xn. Okay, or capital N. So the TSNE algorithm is stochastic neighbor entity. It actually computes the probabilities. As I told you, computing the probability is first step, right? So it computes the probability that is Pij that are proportional to similarity of objects xi and xj. That is whether xi object is similar to xj object or not. If they are similar, then there will be high probability. So depending on the probability, it actually decides whether they are similar or not. Right. So I told you, it is going to find out the probabilities for all those objects, and for each and every object x1, x2. What is the probability they are similar? 70%, 80%. This is what it is going to find out. So I can say that for obviously not I not equal to j, right? Obviously x1 is equal to x1. We need to check whether x1 is equal to x2 or not. X1 is equal to x3 or not. That's what we need to check, right? So for I not equal to j, that probability equation, it actually goes something like this. So probability of j given I, this is how I can read it, right? So probability of j given I is equal to, we can read it like this, exponentiation of magnitude of xi minus xj. Okay, this is the magnitude, take the square of that, divided by 2 sigma square. So sigma I square actually. What is the sigma? Sigma is actually standard deviation, right? What is standard deviation? Standard deviation is something how the values actually deviate from the mean value. That is called a standard deviation. So actually there's a minus sign here. So Pj given I is equal to exponentiation of xi minus xj whole square divided by 2 sigma I square divided by summation of k, and this k should not be equal to I. That is, I if the value of I is 1, then it should not be equal to 1. K should not be equal to 1. So summation of, again, exponentiation, same thing, same term I am going to write over here, xi minus xj, take the square of this divided by 2 sigma square. 2 sigma I square it should be, right? And it should be for all I. For all I, 1, 2, 3, 4, 5, 6, 7, and so on in n. So what's going to happen is, for all I means, obviously here the set the set pi given I is equal to 0. Okay, if I is equal to 0, note that it should be summation sign, summation of j pj given that I is equal to 1. Okay, for all I, they should be for all I. These are some of the conditions which we will try to discuss once we try to compare PCA with PSA. Right, so see, this is the equation of probability which it is going to make use of to find out whether the one point is similar to another point or not, or whether one point is near to another point or not. Right, now as explained by the people who actually come up with this particular equation, the similarity of data point xi to data point xj, I can say, or the similarity of xi to xj is the conditional probability. This is going to be conditional probability pj given given I, and that is nothing but xi would pick xj as its neighbor. Xi would pick xj as its neighbor if neighbors were picked in proportion to their probability density under Gaussian centers at xi. Now the question is, what do you mean by Gaussian? If you people remember NumPy, in case of NumPy we talked about something called as np dot random dot rand, right? np dot random dot rand n, np dot random dot rand in. These two things we are saying. So if you remember, this was uniform probability, right, or uniform distribution, and this was Gaussian distribution. So Gaussian distribution is nothing but what? Gaussian distribution is nothing but the values are centered around 0. That means here it will be negative values, here it will be positive values, and the values distribution will be like this. This is called as Gaussian distribution, where mu is 0 and sigma is 1. And that's what it is talking about. This is 1. So mu is nothing but what? Mean or the average, and sigma is nothing but what? Standard deviation, right? So that's what actually it is talking about. Okay, so in that fashion only you need to pick the values for conditional probability, for calculating the probability whether two objects or 2 points are similar or dissimilar, and you can go and you can actually calculate Pij. Now you can go and you can define Pij is equal to Pj given I plus Pi given j divided by 2n. Obviously, you need to remember any of these equations. Uh, I am able to write it down because as and when we read same thing again and again, definitely we need we can remember it easily, right? But yes, no need to remember all these things. I'm just trying to introduce whatever the mathematics is involved here in case of PSL, so that you will get an idea how probability someone is going to ask you any question based on it, right? So yes, here this is how we can calculate this Pij, and note that this Pij is equal to Pji, and Pii obviously is equal to 0, and summation, as I told you, this summation is equal to 1. So the bandwidth of Gaussian kernels, that is sigma, right, this Gaussian distribution sigma is set in such a way that the perplexity of the conditional distribution equals predefined perplexity using bisection method. So again, see, that is another part. In simple word, what I can say is you should be having your data in this normalized form, and this is actually distributed with the help of Gaussian distribution. That means what? That means it should be centered around 0. That means there will be some negative values and there will be some positive values in your data set. Or data points, I can say some negative points, some positive points. That means if I want to represent in two-dimensional data, I can represent it something like this. So some points will be here, some points will be here. So positive as well as negative, both of them will be here, right? So that's what actually it is trying to represent. So basic point is that it makes use of condition probability. Now, if you go and if you try to discuss or if you try to compare this particular algorithm, this PSNE algorithm with PCA, let's try to talk about these points now. Now, if you talk about this, both of these differences between both of these, right? So let's see that. Let's see the difference between PSNE and PCA, principal component analysis. Okay. So, for example, now let's try to understand from the start itself. Why did we actually discuss PCA algorithm? So obviously, or what is the purpose of these techniques? What is the purpose of understanding or discussing dimensionality reduction techniques? What is the purpose of this? Let's try to discuss that particular thing. Right? For example, what if, just imagine that what if you have hundreds of features, 500 of features, or data points in a data set, and you want to represent them in two-dimensional or three-dimensional space, right? So these are the two common techniques which can be used to reduce the dimensionality of a data set. That's what I discussed yesterday. While even though they are used to reduce the dimensionality of the data set, but still they are used to preserve the most important information in the data set, right? So these PCA, these two algorithms, PCA and PSNE, are the two algorithms which can be used for dimensionality reduction. Now, what are the goals actually? What are the goals for reducing the dimensionality of the data? Why to reduce the dimensionality? Even though I have actually discussed that you will get your model in a less time, processing will be faster, but obviously there are some other reasons also why these kind of dimensionality reduction techniques are important and why are we actually discussing about them. So maybe you can go and you can preserve as much significant structure or information of the data which is present in your high dimensional data as possible in the low dimensional data representation also. So whatever the information which is there in high dimensional data, more or less, somewhat less, but yeah, obviously not. You are not going to that. You are not going to use much of the information, even though you are trying to reduce the dimensions of the data, but still will be able to maintain same kind of information, even though you will be representing the same data in low dimensional space. Okay, so if you represent that data in low dimensional space, obviously it is going to increase the speed of the processing. And obviously, as if you go and if you try to convert your high dimensional data into low dimensional data, right, what will happen? What is another thing? Because of this, there will be increase in the interpretability of the data, right? Because we know that it is more interpretable. Low dimensional data is actually more readable as compared to high dimensional data. So that's again one of the advantages of using converting high dimensional data into low dimensional data. Now, obviously, minimizing information loss of data due to dimensional reduction, we can say. So information loss, it also can be minimized. Okay, so that's what we have seen. What are the PC and PSNE, and what is the difference or similarity between the two? That also we will see. There are some similar points also. So both PCA as well as PSNE, as I told you about this PSNE, that it's unsupervised. So whether it's a PSNE or whether it's PC, both are unsupervised dimensionality reduction techniques. Both techniques are used to visualize high dimensional data to lower dimensional space. This is the similarity between both of them. Okay. Now talking about PCA, we have seen that as it's an unsupervised, but it's a deterministic algorithm which is used for feature extraction as well as for visualization. So this PCA is actually used for feature extraction, okay, as well as it can be used for visualization. This is the use of PCA. Another thing about PCA is that it applies linear dimensionality reduction technique. You try to understand what it applies is it applies linear dimensionality reduction technique. this PCA apply this particular technique, where the focus is on keeping dissimilar points far apart in a lower dimensional space. And what else it does is it transforms original data to new data by preserving the variance in data using eigenvalues. So what it does is it preserves the variance in the data. Right? Yesterday, as we talked about that mathematical equations, right? I shown you in that PDF in that IPY and V5. It makes use of eigenvalues and eigenvectors. So see, it actually what you can say, it preserves the variance in the data using this eigenvalues concept, right? But there is one more point about PCA is that outlier values. Now you are aware about outliers. So outliers actually impact principal component analysis. This is one of the important points about PCA. Outlier values actually impact PCA. Now, if you talk about this particular algorithm, PSA, so it's also unsupervised. It makes of unsupervised learning. It is randomized algorithm used only for visualization. So see, it is used only for visualization, whereas PCA is used for feature extraction as well as visualization. That's the basic difference between PSNE and PCA. Now PCA, the PSNE can it actually applies a non-linear dimensional reduction technique. So it applies non-linear dimensionality reduction technique, whereas PCA applies linear dimensionality reduction technique. Just try to understand this. Where in this case the focus is on keeping the very similar data points close together in lower dimensional space. Okay, in case of non-linear dimensional reduction technique. Now talking about TSNE, it uses uh, heavy-tailed. There is something called as key distribution. I told you. So it makes use of heavy-tailed student key distribution technique to compute similarity between 2 points in low-dimensional space, rather than using a Gaussian distribution. Whereas this actually makes use of Gaussian distribution, PCL, right? So it actually helps. Key distribution actually helps to address the crowding and the optimization problems. Again, that's a different point. Actually, you don't have to worry about that. But yes, it makes use of something called as students key distribution. This is actually a technique. Okay? Student key distribution is a technique which is actually used by TSN. Another point about TSN is that outlier values, or I can say outliers, do not impact TSN, whereas outliers impact PC, but outliers do not impact TSN. That is the bigger advantage of this TSNL. So key distributed stochastic neighbor embedding is unsupervised machine learning algorithm for visualization. Remember that. And how it works actually. So talking about the steps in case of TSNL algorithm. So first step is going to be TSNE, for example, you have some data set, maybe in high dimensional data set, in the data will be in high dimensions, right? So, for example, this is the first dimension. Let's imagine this is another dimension, and so on. Like this, you have number of dimensions. So, I'm representing it like this. Okay, number of dimensions are there. So, it's your high dimensional data, and suppose it looks something like this. These are your data points somewhere here, somewhere here, and somewhere here. Right now, suppose now what it is going to do is, suppose this is xi. This point is xi. Right. Let me just try to. This is the point. Now, what's going to happen is this PSNE converts high dimensional Euclidean distances or Euclidean distances between data points. Suppose this is xi and this is xj. So it is going to make use of Euclidean distance to find the distance between them, and then it is going to find out the probability of j given I. Something like this it is going to find out. Okay. So now xi would pick xj as its neighbor based on the proportion of its probability. Uh, Maybe under Gaussian centered at point xi. So here they are going to find out that sigma I, which is the variance of the Gaussian, which is actually centered at data point xi. So the probability density of a pair of point is proportional to its similarity. So what it is going to do, it is whatever the formula I have shown earlier, it is going to make use of that particular formula and it is going to find out the probability. And later on it is going to find out Pij is equal to all these things. Pj given I, it is going to make use of that. Pi given j divided by 2n, and it is the number of records, number of observations. And once that probability it finds out, the next step is going to be what? In the next step, it is going to map each point in high dimensional space to low dimensional map based on the pairwise similarity of points in high dimensional space. So the low dimensional map will either be a 2-dimension or 3-dimension map. So it is going to look something like this. So the higher dimensional data will be converted into 2-dimensional space, for example, or lower dimensional space or lower dimensional map. So those points, suppose they will look something like this. So this is suppose one point, this is another point, there will be some other point here, there will be some other point here, something like this, some other point here. And earlier it was suppose maybe you can think of these all these points somewhere here, okay, and now it is going to look something. Suppose this is your y point yi, this is your yj suppose, okay. So it is going to look something like this. Maybe some more point, one more point is here. So this is the data in low dimensional space, you can say. So yi and yj are low dimensional counterparts. I think these two are yi and yj. They are low dimensional counterparts of high dimensional data points xi and xj. So whatever xi and xj were there, their low dimensional counterparts are now yi and yj. They are replaced. So we compute the conditional probability here, which is centered under quotient centered point. Okay, and once that is computed, once that conditional probability is calculated, then step 3 is going to be to find out low dimensional data representation that minimizes the mismatch between pi and qi. So whatever qi value we are going to get, we are going to compare those pi and qi value in the first step. Again, so it is going to make use of something called as KL divergence. So I told you about KL divergence, right? Kullback labeler divergence. Again, it's a technique actually which can be used to find out what we can say, as we need to find out lower dimensional data representation which minimizes the mismatch between pi and qi probabilities. So with the help of gradient descent, right? So in that case, this KL divergence is going to come into picture, right? So here PSNA actually optimizes the points in low dimensional space using gradient descent. Now what is gradient descent? So gradient descent is actually a technique which helps to find out the minima. Now, what do you mean by minima? So you might be knowing about derivative, right? So I don't know whether people are aware about or not. The what is the practical application of derivative actually? So derivative we always make use of to find out minimum value. See what happens is, suppose you have data points like this. Okay, now uh, we want to find out the error, and obviously ideally the error should be minimum, ideally it should be 0. Suppose error is here, then we will take the derivative of that. Now error is here, again we will take the derivative, now it is here, now again we will take the derivative, now it is here. We'll go on taking the derivative again and again till we find out the minima or minimum value. Okay, so yes, local and global minima we call it, but again local and global minima, again that's separate concept actually. I'm just trying to talk about gradient descent. So whenever we say gradient descent, descent is going to be decreasing and gradient is but we, so that's a practical application of derivative. We make use of derivatives to find out minima, right? So maybe local minima or global minima. That's a different story again. So that is actually called as gradient descent method. So whenever I discuss linear regression, in that only I explain this gradient descent, because all these methods are actually used for almost all the algorithms in machine learning and data science. Okay, so when we minimize the KL divergence, it actually makes QI physically identical to PI. So the structure of the data in high dimensional space will be similar to structure of the data in low dimensional space. So that will be actually this, the structure will be taken care by this KL divergence. That's the use of this KL divergence. We cannot discuss this particular in detail actually. So yes, this is how one can make use of this KL divergence, and this is how one can make use of this PSNE algorithm for dimensionality reduction technique. If you really, if you people want to apply the PCA algorithm as well as PSNE algorithm on some data set, I will suggest that you go and you search for a data set which is called as MNIST dataset. MNIST dataset is a dataset of images, images of 0, 1, 2, 3 till 9. So images of the numbers. You go and you make use of that dataset and apply either PCA. You apply PCA as well as PSNE algorithm on both the dataset, right? So and this is free actually. You can go and you can download this dataset. If you just Google, you will be able to download this particular dataset easily. So I would suggest, if you are really interested, go and try to implement both the algorithms with the help of PC, with the help of this particular dataset. Okay, and maybe even as we have some more session tomorrow, otherwise I will also show how to apply PC or maybe MNIST on the how to apply PC or TSN on MNIST dataset. Okay, so this is an introduction about the last topic, that is PSN algorithm, which was remaining from the fifth one. Okay. So that's all actually. We have discussed all these points from unit 1 and unit 2. Maybe tomorrow what I will do is I will show you implementation of PCA, and if we get time, we will try to see the implementation of PSN. So at least we will try to make use of a simple Python code. We will try to implement it in Python, and just I will try to show you execution of both the algorithms, PSN as well as PCA. Right? I hope you got a basic idea for both the algorithms. If anyone any doubt, you can ask. Otherwise, we will stop. Okay, any doubt, anyone? No? Okay, then you can send your numbers and names and we'll stop it.